we've got 3i Atlas updates, our best shot yet to clearly see the third interstellar object ever detected passing through our solar system.
Most comets were born in our solar system, but in 2025, astronomers spotted something that broke the rules, an object moving too fast to belong here.
And that is something that cannot be explained just by observing. It's really the first object moving so fast at 60 kilometers per second.
This is 3i Atlas, an interstellar wanderer that may hold clues about planets orbiting distant stars. In this video, we break down everything we know and everything we don't about the cosmic intruder that has scientists racing against time. A cosmic stranger revealed. On a quiet night in early July 2025, at an observatory nestled in the dry, clear skies of Chile, something unexpected appeared on a telescope feed. The Atlas system, short for Asteroid Terrestrial Impact Last Alert System, was running its usual sky survey when one of its telescopes picked up a small moving object just beyond the orbit of Jupiter. It looked like a faint dot, slowly shifting across the stars. Nothing unusual at first glance. Objects like this show up all the time in sky surveys. Asteroids, long-period comets, distant icy bodies, space is full of these travelers. Within hours of its discovery, astronomers were already intrigued. The object's motion didn't fit the profile of a typical comet or asteroid bound to the sun. As the data rolled in and orbits were calculated, it became clear. This wasn't just another solar system body. This object was fast. Really fast, traveling at about 70 kilometers per second relative to the sun. It was moving well above the escape velocity at its distance. Anything moving that fast can't be gravitationally held by the sun, which meant it was just passing through. This object wasn't from here. Astronomers quickly confirmed what the numbers suggested. The object had a hyperbolic trajectory. Its orbital eccentricity measured above 6. For context, circular orbits have an eccentricity of 0. Ellipses fall between 0 and 1, and parabolic escape paths sit at exactly 1. Anything greater than 1 means the object isn't orbiting at all. It's on a one-way trip through the solar system. With an eccentricity over 6, this object wasn't just interstellar. It was flying in from deep space with incredible speed. The object was officially named 3i Atlas, and each part of the name tells a story. The 3i shows that it's the third interstellar object ever discovered, after 1i Oumuamua in 2017 and 2i Borisov in 2019. Atlas comes from the telescope survey that first spotted it. Its longer label, C 2025 N1 Atlas, gives even more detail. The C means it's a comet that won't return since it's non-periodic. 2025 is the year of discovery, while N1 means it was the first new comet found in the first half of July, with the letter N marking that specific half month. In other words, the name isn't random. It acts like a code, packing the comet's identity and history into a single label. Within 48 hours, observatories worldwide began turning their instruments toward this new cosmic visitor. Teams started measuring its brightness, analyzing its spectrum, and plotting its course. The early signs hinted at a possible coma, a halo of dust and gas that suggested the object was shedding material. That was a strong clue that it wasn't just a rock, but a comet, an active, icy body reacting to sunlight. And that matters, because comets, especially interstellar ones, carry pristine material from the birthplaces of planets. They're time capsules, frozen remnants of the early days of star systems. With 3i Atlas, we're not just looking at a comet, we're looking at something that likely formed around a distant star, was ejected into space, and then wandered through the galaxy for millions or billions of years before arriving here. Finding it wasn't just a stroke of luck, it was the result of evolving technology. Atlas was built to detect potentially hazardous asteroids, but its to scan large portions of the sky quickly made it ideal for catching fast-moving visitors like this one. And the infrastructure of rapid data sharing and international coordination allowed researchers to confirm its interstellar nature almost in real time. In a sense, 3i Atlas arrived at just the right moment. With improved observational tools and growing experience from previous discoveries, astronomers were more prepared than ever. The third interstellar object wasn't going to slip by unnoticed. It had our full attention from day one: light, ice, and chemistry. Once astronomers confirmed that 3i Atlas was indeed interstellar, the next priority became clear: figure out what it's made of. Because if this icy traveler formed around another star, possibly in a solar system nothing like ours, then its composition could reveal entirely new chemistry. The first step was analyzing its light. As sunlight reflects off the surface and filters through its halo, or coma, it carries clues about the object's materials. Telescopes around the world began collecting spectra, breaking that light into its component wavelengths to see what chemical fingerprints might appear. Early observations suggested something important. This object wasn't just a rock. A faint fuzziness surrounded the nucleus, hinting that it was releasing gas and dust. That activity indicated it was a comet, a body made of ice, not just stone. But the activity started earlier than expected when the object was still far from the sun. That was a sign that the ices within it are particularly volatile, possibly including carbon monoxide or other compounds that sublimate at lower temperatures than water. As the comet moved closer to the sun, that coma grew. The pressure from sunlight and the solar wind began sculpting a tail made of particles escaping from the surface. Observatories reported that the comet's brightness varied slightly over time, likely due to its rotation. These shifts suggested the object had an irregular shape, possibly elongated or lumpy, spinning slowly as it moved. Estimating its size proved tricky. With comets, the brightness you see isn't just from the surface. It's also from the cloud of gas and dust that surrounds it. Scientists estimate that 3i Atlas is somewhere between 5 and 50 kilometers wide. If the upper end of that range is accurate, it could be the largest interstellar object ever observed. Its color also told a story. Data from various observatories showed that it reflects more green and blue light than many typical comets. That might indicate the presence of certain organic compounds, molecules built around carbon, possibly similar to those found in meteorites and comets within our own solar system. These molecules aren't alive, but they are important. They represent the raw ingredients for life. And finding them in an interstellar comet suggests that the building blocks of life might be common throughout the galaxy. Still, the composition of 3i Atlas remains something of a mystery. The spectrum showed hints of carbon-based molecules, but also strange features that don't match known compounds. It may be that we're seeing materials formed under conditions we've never studied. Temperatures, pressures, and radiation levels that shape this object long before it ever entered our solar system. A hyperbolic path through our system. When we think of objects in the solar system, we tend to picture them orbiting the sun in smooth ellipses. Planets, moons, asteroids, and comets all tied to the sun's gravity. But 3i Atlas breaks that mold completely. From the moment it was discovered, its motion revealed a story of speed, freedom, and interstellar origin. The key clue came from its orbital shape. Most solar system objects follow elliptical orbits, looping around the sun in paths that repeat over time. But 3i Atlas is on a hyperbolic trajectory, open-ended, not looping, and returning. This means it's not gravitationally bound to the sun. It entered our system from deep space, and it's on its way back out. How do we know this for sure? It comes down to eccentricity, a number astronomers use to describe the shape of an object's orbit. An eccentricity of 0 means a perfect circle. Numbers between 0 and 1 describe increasingly stretched ellipses. A value of 1 marks a parabolic escape trajectory, the exact threshold for breaking free of the sun. But 3I Atlas doesn't just nudge past that line. Its eccentricity is over 6, something we almost never see. That figure alone makes it unmistakably interstellar. At the time of discovery, 3I Atlas was moving at roughly 70 kilometers per second relative to the Sun. That's nearly twice the orbital speed of Earth. At its location near Jupiter, that's well above the local escape velocity. Nothing moving that fast can remain in orbit. It has to be passing through. Its path took it into the solar system from the direction of the constellation Hercules. It entered near the orbit of Jupiter, and it's expected to reach its closest point to the Sun, called perihelion, around October 30th, 2025. At that moment, it will be just inside the orbit of Mars, about 206 million kilometers from the Sun. Unfortunately, it will be behind the Sun from Earth's perspective during that time, which means direct observations will be limited. But astronomers are already preparing to observe it again in early December, once it re-emerges from solar conjunction. Even though it's passing relatively close, 3I Atlas won't have any strong gravitational interactions with the planets. Gravity from planets like Jupiter or Mars will tug at it slightly, but not enough to meaningfully alter its path. Still, this brief interaction with our planetary neighborhood provides a rare opportunity. Astronomers can study how solar wind and radiation interact with a truly foreign object, one not shaped by our Sun's environment. The direction of its approach may also help trace its origin. Astronomers are using its trajectory to model potential stellar systems it might have come from. It's not easy. Interstellar space is vast, and small uncertainties in position can lead to massive differences in origin estimates. Still, early modeling points toward stars in the direction of Hercules. Whether it came from a binary system, a young star cluster, or a planetary system like ours remains unknown. From red to green. Color in astronomy isn't just something you see, it's something you measure. It tells you about temperature, composition, radiation, and more. So when 3I Atlas started changing color as it moved closer to the Sun, astronomers paid attention. It started subtle, just a shift in reflectivity, a slight hue adjustment. But then, in late August 2025, it became unmistakable. The comet had turned green. Telescopes in Hawaii, Chile, Spain, and Australia all reported the same thing. Spectrographs confirmed an increase in emissions at wavelengths associated with diatomic carbon, C2. These carbon molecules are common in cometary comas and are known to fluoresce green when exposed to ultraviolet sunlight. But what made 3I Atlas different was how early and how intensely the color change occurred. The green glow was concentrated near the nucleus, consistent with short-lived molecules like C2, which break apart quickly in sunlight. That means the emissions we're seeing are fresh, newly released material escaping from the surface. It's a direct window into the chemistry locked inside the object since its formation. What's fascinating is that this isn't the only time we've seen green comets. Comet Lovejoy and Comet 46P Vertinen both showed vivid green emissions as they approached the Sun. But again, the timing with Atlas is unusual. It suggests a different makeup, possibly indicating a different birthplace. The environment around its parent star, its radiation field, chemical makeup, and temperature history could have shaped the materials differently, and that's why this change matters. Because this isn't just a visual phenomenon, it's a chemical one. The color gives scientists a chance to ask deeper questions about what kinds of compounds exist in other solar systems. Are these carbon chains universal, or is this a unique fingerprint of a place we've never seen? The shift from red to green may also suggest something about layering. As comets warm up, they shed their outermost layers of dust and ice. That exposes fresh material underneath. Each layer has a different history. Some may have been irradiated by cosmic rays, while others remain protected for billions of years. The green phase could reflect a stage in this peeling process, where mid-layers rich in carbon compounds begin to vaporize. There's even speculation that these changes could be cyclic. If Atlas were a periodic comet, which it isn't, this might hint at a pattern of recurring color changes. But because it's on a hyperbolic path, we get only one chance to see this unfold. Once it leaves, it's not coming back. For now, the green glow of 3I Atlas is a striking reminder that there's still so much we don't know about what lies beyond our solar system. The alien mothership theory. Whenever a strange object passes through our solar system, the same question comes up. Could it be more than just a rock? With 3I Atlas, that question returned in full force. On the surface, Atlas looks like a normal comet. It has outgassing, a coma, and a growing tail. But for some scientists, especially those still intrigued by the mysteries of Oumuamua, appearances aren't enough to close the case. One of the loudest voices in this conversation is Harvard astrophysicist Avi Loeb, who gained international attention for suggesting that Oumuamua might have been an artificial probe. His claims split the scientific community. Critics dismissed it as speculation, while others praised him for daring to ask questions that fall outside the norm. Loeb's real point wasn't that aliens had arrived, but that we need to take such possibilities seriously and design tests that could confirm or rule out artificial origins. With 3I Atlas, the evidence so far points to a natural comet. Unlike Oumuamua, it clearly shows the features of a typical icy body. Still, there are small irregularities that raise eyebrows. Atlas has released material in uneven bursts, creating fluctuations in brightness that don't entirely match expectations. Some of these changes even echo the mysterious light patterns that made Oumuamua so controversial. Loeb and his colleagues argue that this is exactly why science should remain open-minded. He isn't declaring Atlas a spaceship, but he insists we need systems in place to test that possibility whenever something strange shows up. That's the goal of the Galileo project, his initiative to apply rigorous methods to studying unexplained aerial and interstellar phenomena. For now, Atlas is best explained as a comet, but the unusual blips in its behavior serve as a reminder. If one of these interstellar visitors really were artificial, we might miss it unless we're willing to ask the uncomfortable questions. Speculation aside, every interstellar visitor leaves us with something valuable: lessons. To understand where 3I Atlas fits in, scientists look back at the first two objects, Oumuamua and Borisov, and what they revealed about worlds beyond our own. Lessons from the past. While the alien question lingers at the edges, most scientists turn to history, because the best way to understand 3I Atlas is to compare it with the two interstellar objects we've already seen. Each of those visitors taught us something different, and together they begin to sketch the range of what interstellar material can look like. The first, 1I Oumuamua, 2017, surprised astronomers. It flew through our system on a hyperbolic track and displayed an unusual shape and tumbling motion that defied easy explanation. Because observations were limited, Oumuamua raised more questions than answers and showed how little we knew about the variety of objects that wander between stars. The second, 2I Borisov, 2019, was much more familiar. It behaved like a classic comet: bright coma, clear outgassing, and a spectrum that revealed water, carbon compounds, and dust. Borisov reassured scientists that other planetary systems produce icy bodies similar to our own, and it provided a direct chemical comparison to comets formed in the solar system. 3I Atlas now adds a third data point, and it sits between its predecessors. Like Oumuamua, it follows a fast, unbound path through the solar system. Like Borisov, it clearly outgasses and shows comet-like chemistry. But Atlas also brings new hints: early color shifts, volatile-driven activity at larger distances, and brightness variations that suggest there are compositional or structural differences we haven't yet cataloged. Taken together, these three discoveries point to one key idea. Interstellar objects are diverse. Some may be rocky, weird-shaped fragments shaped by violent events. Others are icy comets, rich in familiar volatiles. Still others may contain combinations or compounds we've never studied in detail. Mapping that diversity tells us about how other planetary systems form, evolve, and scatter material into interstellar space. Catching Atlas early matters. The timing and quality of observations determine how much chemistry and physical detail we can extract. Better spectra, longer monitoring of brightness and tail behavior, and coordinated global campaigns all improve our ability to compare objects and refine models of their origin. Over the next years, researchers will reprocess Atlas's data, compare it to Borisov and Oumuamua, and run simulations to narrow down possible birth environments. Finally, there's the practical fallout. Each new discovery improves detection systems and mission planning. As surveys get faster and telescopes more sensitive, astronomers will spot interstellar visitors sooner, giving more time for detailed study and potentially for fast response missions. Even if a chase mission to Atlas wasn't feasible, the lessons learned now will shape how we design instruments and strategies for the next rare visitor. In short, 3I Atlas is more than an isolated curiosity. It's a missing link in a small but growing sample that will let scientists build a taxonomy of interstellar objects, one that can reveal how common certain ices and organics are, and what that means for planet formation and the raw ingredients of life across the galaxy. Eyes on the sky. The global effort to monitor Atlas began just hours after its discovery. Observatories across 6 continents and several space-based instruments turned their attention to the object. Telescopes like the Gemini Observatory, the Keck Observatory, and even smaller university scopes joined the effort. Each one plays a unique role. Some capture high-resolution spectra to analyze the chemical makeup of the coma, while others track its motion and monitor for unusual behavior. One key facility stands out: the Vera C. Rubin Observatory. Though still in its early operations phase, Rubin was designed with moments like this in mind. Its massive 3.2 gigapixel camera and sweeping sky coverage allow it to scan the entire visible night sky every few nights. That makes it ideal for catching fast-moving objects, especially rare, fast interstellar ones like Atlas. The Rubin Observatory is part of a larger movement in astronomy: time domain surveying. Rather than focusing on a single target for long periods, Rubin and similar instruments scan wide sections of the sky repeatedly, catching changes in motion, light, and structure over time. This approach is revolutionizing how we detect comets, asteroids, and transients. Alongside the giants like Rubin and Keck, small and mid-sized telescopes are making big contributions. Amateur astronomers with high-quality equipment are helping monitor brightness and position. Some are even capturing time-lapse sequences that show changes in coma size and tail structure. With so many eyes on the sky, the data collected is not only diverse, but also constant. Every minute adds resolution to our understanding. There's also a strong collaborative network behind the scenes. Scientists use central repositories like the Minor Planet Center and the International Astronomical Union's Telegram service to update positional data, share brightness curves, and flag anything unusual. When one team sees something odd, a sudden spike in brightness or a deviation in trajectory, they alert the rest of the community, prompting coordinated observations. Instruments on space telescopes like Hubble and the James Webb Space Telescope may also get involved. These provide the clearest views, unaffected by Earth's atmosphere. While observing time is precious and limited, Atlas's rarity could justify special sessions. If approved, Webb could offer infrared spectra that would reveal the comet's thermal profile and possibly detect exotic ices that ground-based telescopes might miss. By early 2026, 3I Atlas will fade into the darkness beyond Mars, moving too far and too faint to track. Every observation before then matters. The information collected now will be studied for years, maybe decades, as scientists build models of interstellar chemistry, motion, and composition based on this one brief encounter. So the eyes remain on the sky. Dozens of observatories, hundreds of scientists, and even backyard astronomers are all watching this icy visitor as it flies by. Not because it's dangerous, but because it's rare. And in the vast stillness of space, that's reason enough to pay attention. The final exit. The story of 3I Atlas doesn't end with its departure. In many ways, that's where the real work begins. Because once this icy visitor exits the solar system for good, it leaves behind more than just a vapor trail and a glowing coma. It leaves us with data, with questions, and with a broader sense of what it means to live in a galaxy filled with motion. As 2026 approaches, 3I Atlas will fade beyond the reach of even our most powerful telescopes. It will be just another speck in the deep sky, indistinguishable from the billions of other icy bodies drifting between the stars. But unlike those anonymous travelers, this one left a record, a traceable, measurable fingerprint that scientists around the world will study for decades. First, there's the physical data. Every light curve, spectral reading, and position measurement will be logged, archived, and fed into models. These models don't just describe Atlas, they expand our understanding of cometary behavior, chemical variation, and solar system dynamics. By comparing Atlas's motion and composition with previous interstellar visitors like Oumuamua and Borisov, researchers can start mapping out a kind of taxonomy. What types of materials are common in other systems? How do they behave under solar radiation? Do they share features with comets from our own backyard? And then there's the deeper work, the part that comes after the headlines fade. Scientists will reprocess the data with new techniques, run simulations to backtrack its origin, and even theorize about the kind of system it came from. Was it ejected from a young planetary disk? But Atlas's exit also shapes our future. Each time we spot an interstellar object, we refine the systems that make those detections possible. Sky surveys get faster, algorithms get smarter, and collaboration across institutions grows stronger. By the time the next one comes around, we'll be better prepared. We may even have probes on standby, ready to launch and intercept. There's already growing interest in missions that could one day chase down these fleeting visitors. Concepts like the ESA's Comet Interceptor are designed with objects like Atlas in mind. The idea is to wait in space, stationed and ready. So when something unexpected enters the inner solar system, we can go to it, instead of just watching it go. The significance of 3I Atlas also runs deeper than science. It's a humbling reminder of how dynamic the cosmos really is. We often think of our solar system as a closed, well-mapped arena. But Atlas proves that the space between stars is full of motion, and that sometimes those distant objects come right through our backyard. And when they do, they bring stories. Stories from other stars. Stories we're just beginning to decode. So while Atlas may be leaving, its impact is only beginning. It will spark dissertations, shape models, and refine telescopes. It will serve as a reference point for future objects, and it will remain a symbol of how far our observational reach has come. In the silence of space, 3I Atlas continues its journey. We don't know where it will go next, or whether it will ever pass close to another star. But we know this. For a brief moment, it passed through our skies, lit up our sensors, and deepened our understanding of the universe we live in. Thanks for watching. If you liked the video, hit that like button, subscribe for more, and drop a comment below. I'd love to hear your thoughts. See you in the next one.